So today is all about light matter and light tissue interaction. Okay? As you remember, based on our scheme, last time we talked about light sources. Can somebody tell me one interesting thing they discovered about different light sources on Monday? Anybody? Yes.
Light in different ways. Use a lot of heat.
Okay. Some use a lot of heat, some don't. Use light in different ways. Okay. Anyone else? Yes.
That fluorescent light actually uses UV rays and then transfers them into visual light. I thought that was interesting.
Okay. Good. Good. And how fluorescent lights work? Any one last comment? Anything else?
I was interested to learn how LEDs work. That was interesting.
Okay, sounds good. Great. Okay, so we also started talking about how light can interact with matter, and today we're going to continue that by interacting with something biological, your hair, and we're going to talk about all kinds of other ways in which light can interact with living tissues. To do things like remove tattoos and blast kidney stones, things of that nature. Okay? So the main point of the day will be we're going to measure your hair thickness using diffraction. We're going to look at how light interacting with tissue can be transmitted, reflected, refracted, scattered, and or absorbed, and can all happen simultaneously. And we're going to focus in on absorbed light because that can cause heat, chemical conformational changes, fluorescence, phosphorescence. And that tends to be when photons are absorbed, it tends to be when a lot of interesting things happen. Okay? And we're also going to look at how laser light can interact with tissue and have thermal effects, mechanical effects, photoablative, and photodynamic effects. Okay, we're going to look at all those 4 different ways in which laser light interacts with tissue. But the first thing we're going to do, probably for about 45-50 minutes, is you're going to collect the data for your first lab report, which has to do with measuring hair thickness. Now, you're going to see some very high-tech devices out here. We have Lego laser holders. And we have wooden laser holders. Okay? Just a couple of different generations of materials. Okay? We have hair card holders, and we have hair cards, which most of you already put a hair across one of these things. Okay? Now, because I only have 6 of these, I created another kind like this that you'd actually have to tape your hair across this. Okay? But I'm sure you guys can figure that out. And I gave you some extra thin Legos as spacers in case you need to move your hair up or down in relationship to how the laser fits on these things. Okay? When you have your card, it's easy because you can move it up and down inside this holder. You guys are going to divide up into 8 teams. So there'll be 3 people on most teams except one team will have 2. I think, because I saw yesterday there were 23 people. There was an extra person. Let me see. Doesn't look like... that's what was going on. Okay. I was wondering about that. Okay. So actually we have 22 people, so there'll be one group of 4. So there'll be 7. So only one of the groups will have to use this approach, and you can use 2 or 3 of them if you like, because you'll have different people in your group. Now, what you're basically going to do is you're going to stick your card inside the holder, and you're going to have your laser. There's a spot here for the green or blue laser, and there's a spot that can be also used with red lasers, unless you have this flat red laser, then you can use it here. You're basically going to measure out a distance, and I'll give you more specifics on this in a moment. Measure out a distance, project onto the wall. You've got some white paper over there that you can project onto, where you can write your data. And you'll basically be holding your laser really steady, shining it on the light, and looking at the pattern that's generated. Okay? And you'll be measuring some things out of that pattern that's generated. I have red lasers and green lasers. There's, I think, 10 lasers overall, so there'll be plenty. You'll have to switch around. I expect everyone to test every person in their group's hair with both the red laser and the green laser. Some of you, if you end up having time, will get to use the blue laser. Okay? The blue laser has a very bizarre battery in it, so it doesn't have a very long life remaining in this battery, is my fear. So I don't know if all of you will get to use the blue laser. Okay? But those of you who are done with the other measurements can then come and ask me for the blue laser. These, by the way, cost like $400, these blue lasers. They're much more expensive. And I'm going to, while you guys are doing your data, I'm going to pass out 3 sheets which help you understand how you're going to write up your lab report. One of them is called the Format of Laboratory Reports. Okay, it explains the different sections that are expected in your laboratory report. It's 4 pages, big printing. Then there's the checklist for laboratory reports, which is basically like a little cheat sheet for this. It gives you a sense of one of the main ways in which we're going to be reviewing your reports and how your peers are going to be reviewing your reports. And lastly, we have the communicating with graphs. And this one is all about mistakes you can make when you're doing your graphs and things to avoid and things to try to do to make the most effective graphs you can of your data. Okay? I don't expect you to follow every single thing in here to a T, but these are suggestions that will help you get the best lab report possible. Okay? I'll pass these out while you guys are doing the experiment. Yes?
Are these also available on SmartSite?
Your
website, I mean?
These checklists are not right now. I'm going to hand them out to you. I have to think about that. I'm not sure I want to put them up there quite yet. Okay, so why can we measure hair thickness using diffraction? Okay. Lasers give out electromagnetic radiation, visible light in this case. Photons behave as both particles and waves. We're taking advantage of the wave properties of photons to figure out, using diffraction, the thickness of your hair. You guys remember that if I shine a laser on a hair, I'll get a pattern of light and dark. This is supposed to signify light, dark, light, dark, light, dark. Okay? This is just a way of showing that kind of a pattern. This is an actual representation of that pattern. See the bright spot in the middle, dark, light, dark, light. You guys see that pattern? You guys remember seeing that pattern the other day? Okay? So the equation that tells you the width of the hair is this equation right here. The width of the hair, A, times the sine of the angle is equal to m times the wavelength of the light you used. Okay? Let's go through each one of those for a moment. So, you're going to try to solve for A. That's what you're trying to find. Okay? Sine of the angle. This is the angle. The angle is the angle between the straight line where the bright spot is, straight line that comes this way, and the line that goes from the hair to the first dark spot. Okay? So effectively you've got, if I were to magnify it quite a bit, and I'm the hair, the laser shooting from behind me, I've got the straight line that goes where the bright spot is on the screen in front of me, and then I've got the first dark spot, and this is the angle. Okay? Sine of theta. That's the angle. And then that equals to m, and in this case, if I choose to measure the first dark spot, m equals 1. If I choose to measure the second dark spot, m equals 2. If I choose to measure the third dark spot, m equals 3. Okay? Just depends on which one I'm using. Times the wavelength. The wavelength you can read on the laser. The laser has a little tag, and it'll tell you the wavelength. It'll tell you the wavelength here in nanometers. Okay? The really important thing today is to make sure you're consistent with your units. Okay? Now, how the heck are you going to figure out this angle? It's easy to figure out this because it's written on the laser. It's easy to figure out this because it will depend on which one you decide to measure. But how do you figure out that angle? Well, that angle can be figured out this way. The tangent of the angle is equal to x, the distance between the bright spot and whichever minimum you're using, divided by the distance from the hair to the wall. So you're going to have to know the measurement from the wall to your hair and try to be very accurate with that measurement. And you're going to have a very accurate measurement of from the center of the bright spot to whether you're using the first dark spot, the second dark spot. Some people will choose to measure from dark spot to dark spot and divide in half. That's perfectly reasonable. There's a lot of different techniques you can use, but you have to make sure you write down what you use because that'll help you in the report. Yes?
Are you measuring to where the dark spot begins or like where the middle of the dark spot?
The middle of the dark spot. You always measure to the middle. The middle of the center here, right in the center, and then to the middle of the dark spots. Okay? So do you guys think that measuring the first dark spot will lead to more accurate results, or measuring the second dark spot will lead to more accurate results? And why?
First one is probably going to be easier to find and more narrow or something, so that would probably get more accurate results.
So this is going to depend. Okay, we're going to try to make the room as dark as possible. With the green laser, you're going to get brighter space. When you're making a measurement and you're using a ruler, a variety of different rulers up there, always measure in centimeters, by the way, don't measure inches. When you make a measurement, and you make a measurement that's this big, versus a measurement that's that big, when you make a larger measurement, you're likely to have less error, if you can see where the measurement should be. So if the image is bright enough, and you can see where that second dark spot is, or that third dark spot is, you're going to get a more accurate measurement, because the error decreases as you go out to a larger measurement, because of the way the division works. Okay? You guys get that? So, would you rather be 1 meter away, 2 meters away, 3 meters away? And how might that affect your readings?
Well, you can go as far away where it's still bright enough on the wall to see.
And why would you want to do that?
Well, the further away, it's the same thing. The bigger it is, the less error it's going to be.
This number will be bigger, there'll be less error, and this number will be bigger, there'll be less error. Okay? So I have 2 tape measures out there, and I've given you what 1 meter is equal to in inches, 2 meters, and 3 meters. Okay? My suggestion to you is to see how the brightness looks and see how far you can go. These are the 2 standard tape measures. You're going to be projecting against one of these walls, or one of those walls, or one of the back walls. Okay? You pick the wall that you want to project on. There's some scrap paper over here, and there's some. Used to be some masking tape.
It's behind you. On the table.
Oh, okay. There's a masking tape here, and you can tape these onto the wall. My suggestion is to tape these on the wall and collect your data. Collect your data. If you're welcome to take more, you're welcome to use your own white paper, it doesn't matter. Okay? But remember that you're going to be utilizing this data. It's much easier to have a piece of paper on the wall, project this on there, and just draw the first dark spot is and where the center is. Then it is to go here with the ruler while your partner's over there slightly jiggling the laser. Okay. It's very difficult, as you'll soon see. So the best thing to do is just mark it on the paper and then later measure. Okay? Now you're going to have to keep moving the paper because you're measuring different people's hair and you're measuring different colors. So don't get your paper up there and tape it all around really nicely. Just give yourself one piece of tape so you can quickly move it up or down a little bit and you can write other people's name. Okay? And we're going to try to get a sense of what numbers you're getting by 11 o'clock. Okay? A little before that. Or if you get a number already and you want to ask me whether it makes some sense, we'll talk about it. Okay? Are there any questions? Okay? And remember, you're going to be then figuring out a way to represent this information and be writing up a report on it. So make sure you have a good idea of how you're doing the experiment and the data that you're using this stuff. Okay? So, we're going to divide up into 7 groups. One group will have 4 people. So go ahead and divvy up and go ahead and grab your materials. And start. Well, again, you're using lasers. Be really careful. Don't try on anyone. Don't try on anyone's eyes. Okay? Be very, very careful. I'm just going to get another picture of you guys. I'm going to get another picture.
Leave it at red. Just get the next.
Welcome to my world. Actually, up right now. Okay.
We have 4 green lasers, 4 or 5, so you're exposed to you're all brown, so you just have the silver ones.
You're the one who wants to switch.
Don't share it so much. Like, all right now. I'm not great.
Sorry. I thought you want to grab it.
Oh, it's not that last 11. That was 11. It wasn't. This is it. It's 11. We're going to go back on the
Why don't we do the plastic thing?
Put one word.
This is maybe very confusing about this.
I know.
That's where the box has to be. So that way. Get one to begin.
Okay, so what are we supposed to do?
So those two are red. We'll mark those to the green house later. No, we're just doing the like every line every time it's like this are
No five. Alright,
yeah, and then you do mine, I do yours. like to top and bottom. That way you have something to compare. I don't have to see it.
Okay, so then you
I just do like, you see how you do top trees? Do like, oh, well, I didn't do it. Just we have something to compare.
Did you mark the center spot?
There's a green laser available.
Probably kind of like stretch, like
Turn it off. You need to shine the next one. Where it is.
So we should.
Write my name on it. My paper, and then should we haircut it, or should we just put it
I can remember how to do it.
I mean, like my picture.
I'd like to write it down.
well, look at that. It's just once you're writing our lab, probably like writing together, at least with the secret and stuff. What?
Do you want to put writing
Wait, how do I use? Okay, laser.
It looks kind of like Star Wars stuff. It sounds pretty like galaxies and stuff.
Oh, you got it, okay. Come on.
The green laser is back. There should be 4 red lasers.
I can get that.
Do you have an outlet plate? Jim, do you have another red laser we can talk about? You're going to find that your standard hair is going to vary somewhere between 40 micrometers and roughly 250 or 300 micrometers, okay? So there's a big variation in hair thickness. And remember, you guys are writing up your lab reports with the data for yourself, but also data of your classmates. I'm sorry. You're using the data for yourself and the data of your group mates. Okay? But you are making individual reports. So you're each making your own report, but you're using the data from the group. Okay?
So we have to report on their hair as well as our own?
Yes. Okay? You will need their data. Okay? Yours is the main one, the most important, but you're also reporting how you compare with them and what their data is. That's up to you. You can either get the raw data or it's up to you. On Wednesday, you're going to be turning in 4 copies of the report. Okay? Because what's going to happen is we're going to block out the name on top and we're going to pass it out to 3 other reviewers. So we're going to review 1 copy and 3 of your peers are going to review. Yes?
If we're turning 4 copies, should we just turn the 1 copy with the name and the other 3 copies with no name on it?
That'd be great. Yeah, if you do that. Except we still need to know who it is.
Well, if we have 1 copy with the name on it.
That's true. That'll work. 1 copy with the name and 3 copies with no names. That'll work. Good thought. Yes?
In general, when talking about when people are interfacing Haley's hair with this or Haley's hair with this, how do you talk about it?
The best way to do it would be to give the subject a number. So subject 1 or subject A, subject B, subject C. Now, in the directions that I sent out to you, it says that in your title piece you talk about who your lab partners were. And you could have a little, if you wanted to, you could have a code, a key that says subject A is such and such, subject B is such and such. Except if you do that, well, people are going to know who your report is anyway. So it's okay. No, that's okay. You don't have to do that. You can just say subject A, B, and C, but it's up to you. Whatever makes it easier for you.
What's the wavelength of the laser between red and green figures?
Well, so does your hair change thickness? So this is a way to get another measurement.
So do you take the average of the 2?
Well, you got to think about how the error propagates. Because one of them gave you a broader separation than the other. So you have to think about that, take it into account. But that is a perfectly reasonable thing to do. That's how you want to do it. You can also average multiple readings that you might have taken if you took more than 1 reading of the same hair with the same color. Okay? And what we'll try to do after we've gotten all your reports, we'll try to do a class graph of everyone's thickness, hair thickness. But that'll be separate. Don't worry about having to do that. Okay? Okay, so if you have any other questions, feel free to email myself or Professor Shackelford and we'll tell you more. Okay? So let's move on. Interaction of light with biomaterials. We talked about last time that we can have transmission, which is the light just going through the biomaterial. Reflection. Refraction. What was refraction? The angle changes. Basically, the photons slow down when they get into something of higher density. They just slow down. And depending on the angle at which they're interacting with that surface, they will bend further. Okay? Scattering and absorption. Okay? So, the exact amount or how these things are work out in the material was going to depend on the physical and chemical structure of the biomaterial you're interacting with. Okay? So, you can have photons interacting with the matter and they can cause heat. You can heat something up by having the light interact with it. Can you give me an example that you guys feel, hopefully on a regular basis? Sun. Makes you feel warm. Okay, you can have photons going in causing chemistry to happen. What might that be? What do I mean when I say chemistry to happen? Yes? Yes.
Like advanced photosynthesis, they convert the photons to energy that they use to react to the reaction.
So they actually make a chemical reaction happen. I can break bonds, remember? I can cause molecules to get excited, but that usually corresponds to heat. When it's chemistry, it's either usually a conformational change or a bond breakage, things of that nature. I can cause light. I can put light in and I get light out. And we know that that can happen by just straight transmission. How else might that happen? Yes? Fluorescence. Yep, fluorescence, phosphorescence, perfect. And I can cause motion. What might I mean by that? Back there.
You were saying on Monday that
Chris.
you use highly concentrated lasers to push cells around.
Yeah, I can actually trap a cell.
Now, would you use the microwaves where you use the water particles?
You could think of it, if you want to think of it as motion within the molecules, that's fine too. Yeah, the rotations. Yeah, that's another good point. Okay? So, photonic energy can come into a system and it can cause all kinds of other things to happen. Now, we can do electricity too, solar panels, but it's not something that tends to happen in living tissue. Okay, that's why I'm not highlighting it. So, I'm going to talk to you about some ways in which we can use these properties. So the first one I'm going to look at is refraction. Whenever we do microscopy, when we look at things under a microscope, the main object is to see something under the microscope and to see it really clearly. That's why we use the microscope, right? We want to learn about something really small. To do that, we need to be able to see it well. And how many of you have used the microscope before and you put in some pond water or something and things look very dull? Has that ever happened to you? Very plain. There's not much there. Well, you can get something like this as an amoeba here. We can use techniques that take advantage of the light being slowed down inside of a cell to give us contrast in an image. So this is a type of microscopy that allows me to get an image that looks more like this, taking advantage of the fact by using some special optics that it'll make contrast happen when there's a difference in the speed of the light going through the material. Okay? So I get this kind of a pattern. This kind of microscopy tends to give you this halo type of piece, and can be called phase contrast or differential image contrast. Those are some different names for this type of microscopy. And you're going to be getting introduced to different types of microscopy as we go on through this course, especially when we talk about tools. We talked the other day about absorption. Okay? So absorption, photons come in, that energy excites an electron to a higher energy level, and that can manifest itself in different ways. If microwaves are absorbed, it usually changes the way molecules rotate in space. This is what you were talking about a few minutes ago. If we bring in infrared radiation with living things, usually they cause a change in vibration. Okay? Rotation and vibration can both lead to the perception of heat, what we call heat. Okay? In infrared radiation, that makes a lot of sense. Ultraviolet or visible photons, when they're absorbed, are they higher energy or lower energy than the infrared? Higher. Okay? And even higher than the microwaves. Okay, microwave is the lowest. Those will change the way the electrons are distributed within a molecule, and it will often change the shape of the molecule, or potentially even break the molecule. These are those sunglasses that when you go outside, they will change color. Okay? Well, guess how those work? They take in the high energy light that they're getting from the sun, or from any kind of bright surface, and that causes a conformational change in the molecule. That conformational change in the molecule causes them to darken, and it's reversible. If that energy goes away and that absorption isn't taking place, the molecules go back to their natural state, and it becomes clear again. Yes?
How come after one time of those glasses they don't change as well, like they don't go all the way through?
Okay. That's basically because these reactions are all, for the most part, reversible. But over time, some of those structures change in such a way that they can't reverse very easily, or some of them basically get stuck. Okay? So you can imagine over time, as more and more get stuck, the change isn't as great anymore. Okay? Now, usually everything's happening at the same time. So if I have a energy state change that's caused to like ultraviolet or visible, I get an electron jumping energy level. When we make these other lines like this, these are vibrational levels. Okay? And changes within these lines will be changes in vibrational state. And if I were to make even more lines in between these lines, if I were to make little lines like this, little line, little line, those would be representation of the energy change in rotational states. So usually when I jump and I absorb energy, I'm absorbing energy and I'm changing electronic state, which is the high energy state. I'm changing vibrational state, and I'm changing rotational state. All three of those things happen at the same time. But there has to be a place for me to jump with the energy I'm bringing in. Because the molecule that I'm working with can only absorb energy if there's a specific jump it can jump to. If there isn't a jump that corresponds to an electronic, vibrational, and rotational state, it can't go there. So it can only be absorbed if there's a specific jump available for it to go into. Okay? It's not continuous. You have to go to a specific state. And then you can get relaxation through rotations, vibrations, and electronic jumps. Now it sounds a bit confusing. You'll be hearing a little bit more about it as we keep going. So electronic plus vibrational, sometimes they call them vibronic. They're just different names. But when you have these transitions, you're changing usually electronic state, vibrational state, and rotational state. And primarily we only talk about the rotational and the vibrational. I'm sorry, we're going to talk about the vibrational and electronic. We don't tend to talk about the rotational because it tends to be such weak energy changes. So when we're working with light and tissue, these vibronic states, these jumps in energy, can basically cause chemical reactions to happen that don't normally happen. Okay? So photochemical reactions result in the destruction of the original molecule. So in most cases, things are not reversible, like what I was telling you before. When you have the light interacting, it's absorbed and it causes something else to happen. It causes some other products to be created. You can also basically have an absorption of a photon, and there's so many different ways in which those photons relax that you get a release of heat. Okay? So absorption of photons often releases in some kind of heat and other things. So it can result in the heat, it can result in the conformational change, it can result in the molecular change, and all those things can happen simultaneously. And when we want to describe how a certain molecule, sets of molecules are absorbing light, we create something called a spectrum. And that spectrum tells us, shows us energy in one axis, and it shows us the amount of that energy that was absorbed. Okay? So we get an absorption spectrum that says, this wavelength was absorbed a little bit, this wavelength was absorbed a lot more, this wavelength was absorbed the most, this one less, this one less, this one more. It tells us. And by the shape that we get, we actually can see, for example, this is showing you, this green transition here would correspond to this, the red transition would correspond to that, and the blue transition would correspond to that. And when you actually see the spectrum, it would look like this. will look like these blobs. So in a spectrum, you can see the various ways in which electrons have been absorbed to go into different electronic and vibrational states and rotational states. That's what the spectrum shows you. It shows you where those absorptions took place, at what energies. Okay? That's how we learn this. That's how we figure this out. And the way we characterize absorption is by a formula known as Beer's law. Okay? And Beer's law, the way people remember it is, the deeper the glass, the darker the brew, the less of the incident light that gets through. Okay? That's a little shortcut for remembering. But it basically says, I can quantify the amount of light that is absorbed. And I can do that, and it's very specific to a given molecule or a given combination of molecules. The absorption is equal to the extinction coefficient at a certain wavelength. So what this says is, for a specific molecule, I have this very specific number at this specific wavelength. So DNA will absorb at 250 nanometers this much. It's very specific. Then I multiply it times the path length of how much of my molecule I have the light going through times the concentration of my molecule. So you can imagine the absorption increases if I double my concentration. My absorption doubles. If I double the amount of length that I'm passing my light through, my absorption doubles. Okay? So it kind of makes sense. If you were to take some food coloring and put it inside a little test tube, okay? If you put twice as much of the food coloring in the water, not as much light would get through. If you were to take a bigger tube with the same amount of water to food coloring mixed together, not as much light will get through because it's a thicker piece going through. Okay? Does that make any sense? And when we look at specific living tissue, and we look at their spectra, okay, which shows us how light is absorbed by them, if we look at DNA, we can find out something about the DNA. Here's the wavelength, 180 nanometers. This is all in the ultraviolet, up to 300 nanometers. Okay? We can see that DNA that's double-stranded, native, will have a spectrum that looks like this. DNA that's denatured, meaning that it's fallen apart, the two strands are not together anymore, will look like that. DNA at 82 centigrade will separate. At 25 centigrade, tends to be together in a double helix. Okay? And you can use this to figure out properties of how strong those helices stick to each other. I spent my first year in graduate school doing that. I created little structures called hairpins where you would make a piece of DNA or RNA that would be single-stranded, make a loop, and then attach to itself again. And what I would do is I would work for 2 months to get my sample, and then I'd stick it inside a spectrophotometer, and I'd heat it up while I measured at 254 or 260 wavelengths around this region. And I saw it change, and I could tell exactly how much energy was involved in making those bonds in the hairpin, or whether even the hairpin was made. Okay? So you can tell what's happening, changes in conformation, based on looking at the spectrum. Now, in your eyes, you have 4 pigments that absorb light. And depending on how much each one of them absorbs is where we get the idea of what color we're seeing. So, you have one that absorbs blue, and this is its absorption spectrum. Rhodopsin, that's the one we tend to use at night, that we just sense as absorbing, just as seeing light or not light. Then we have a green one and a red one. And depending on how much each one of these pigments absorbs, our brain interprets a color. Okay? These are their absorption spectra. And the last thing I want to tell you about absorption in living things, this is a wavelength, 100 nanometers. This is the equivalent of 1 micrometer or 1,000 nanometers. This is 10,000 nanometers. We have what we call an optical window for living tissue. And what this says is, this is the spectrum of blood. This is how blood absorbs at those wavelengths. This is how your aorta absorbs. This is where water absorbs. So, wherever water has a very low absorption, in this region from here to here, is where we have a good opportunity to study living things directly in living things. So we can utilize the fact that there's not a lot of absorption in this region by water, and we can utilize the fact of this blood spectrum to figure out your amount of oxygen in your blood with that little tool that we made. Okay? So we have a window that tends to be, this would be 200, 300, from about 200 nanometers, 3, 4, 5, 6, 7, 8, 9, to about 900 nanometers, where the absorption of water is relatively low. This is a log scale. It's relatively low, and so we can see other things just based on how they absorb light. Okay? Once we get out here, into this region over here, basically where things like this absorb less than water, then we can't use those wavelengths very easily, because water is always the main thing that we're seeing in something alive. And it blocks us from using those wavelengths. Okay? So the optical window, this is another way to see it. This one has a few more things on it. It has whole blood, epidermis. It shows you the aorta. It shows you the absorption of skin. It shows you all these different things. And these little yellow spots, it just shows you lasers that have that wavelength. So what laser would you use to look at what part of the spectrum? Oh, the keys. Thank you. Okay? So again, this is the optical window that we have. It tends to be from about 200 to about 1,000 nanometers. Okay? And what does it mean to be the optical window? Why do we call it that? Why is it relevant to us? Yes? Yes, basically water is not dominant in that region. Okay? The absorption of water is not dominant. So we can look at the absorption of other specific things inside the tissue. The DNA, the RNA, certain proteins, the blood, the hemoglobin. We can look at all those things in that region just by using light in something alive. Okay? In the other parts of the spectrum, water overwhelms us. It's very hard to detect the signal above and beyond the signal of water. Not impossible, but very hard. Okay. And so, to kind of recap, remember, when light is absorbed, you can have fluorescence. When light is absorbed, you can have heat. When light is absorbed, you can just have it be absorbed and then re-emit it right away. And you can also have phosphorescence. So all of these things happen simultaneously. And depending on the specific molecule, you get more or less of one over the other. And also depending on the conditions the molecule is in, what it's near. Okay? So that's how we get information about what's happening to molecules. Questions about that? So is it possible to have, if I have a set of molecules inside living tissue and I shine light and that light is absorbed, could I have fluorescence and phosphorescence happening? And heating? Is that possible or is that impossible? It's possible. You can have all those things happening. Are they all going to be the same amount? Okay? They're going to vary. There's going to be it's all combinations. Just pick one that we want to look at. Sometimes we pick more than one, but usually we just pick one to look at. Okay. So let's move on now to laser and tissue effects. So laser light can have the following effects with tissue. Thermal, meaning heat things up. Mechanical, like move something. Photoablative. Photoablative just means poof. Means I take that tissue and I make it into vapor. Make it into nothing. Okay? And photodynamic. That means I can have light being absorbed and cause some kind of chemical change. They can cause some other havoc. So, thermal processes. There's three main thermal processes. One is called hyperthermia. What do you guys think hyperthermia would mean? Yes.
Excessive heat.
Excessive heat. So, if I keep living tissue, cells, at 41 to 44 degrees centigrade for 10 minutes or more, I will get some cell death because I'm effectively shutting down some of the enzymatic processes that keep the cell alive. Okay? This is why we're worried about fevers. This is why we're worried that if your temperature is over 40 degrees centigrade for a long amount of time, you start getting delirious and it could actually kill you to get too hot because you're basically shutting down your cell's processes in surviving. So that's kind of the one level of heating up things. Coagulation refers to irreversible necrosis without immediate tissue destruction. So necrosis is cell death. The temperatures reach 50 to 100 degrees centigrade for around a second. Produce desiccation, means all the water is sucked out. Blanching and a shrinking of the tissues by denaturing the proteins and collagen. So, have you guys ever cooked an egg? Okay, that gooey clear stuff. The moment it gets really hot, what does it do? Turns white. Okay, it coagulates. That's the same thing that happens to your tissues. Okay, the proteins inside them will turn like that, and therefore they're no good anymore. You can't use them. They might be edible, but they're no good to you anymore and to the living thing. Okay? And then the last thing is volatilization. Volatilization means that you actually have material that's lost. It vaporizes. It goes away. This usually happens above 100 degrees centigrade, and it can happen very quickly, 1/10 of a second or so. And again, if I were to shine a laser powerful enough to cause volatilization, at the fringes, I'm also likely to get some coagulation, and even up further away, I'm likely to get hyperthermia. Okay? So these things compound on each other. See what I'm saying? If I get one little spot really hot, nearby it's going to get kind of hot, and even a little further out, it's going to get warm. So you have to think, yes?
The lasers that can cause volatilization commonly?
Oh yeah. Yeah, we're going to be talking about them. Lasix, for example, and also whenever you use a laser as a scalpel. Yeah, definitely. Okay? So the thing we want to think about now when lasers are interacting with tissue is we want to think about how much power per unit area is the laser delivering. Okay? Because you can imagine a laser that has a certain power, but it delivers it over a spot this big. How will that differ if that same power is delivered to a spot this big? What would cause, let's say that laser has all that power and it's delivering it to my stomach. Now somebody focuses all that power into a little 1 millimeter spot. What might the difference be in the effect on my stomach? On my tissue? The same power, delivered over this much space or delivered over this much space.
One it might keep you, and the other one probably like burn through.
Potentially it would. Did you guys, I know this is kind of cruel, but did you ever take a magnifying lens to the sun and try to fry a little ant? Has anyone ever done that? Okay, some people are willing to admit it. Okay. Now the sun by itself, the ant's walking around. If I take that much of the sun, or whatever my size of my lens is, and I concentrate it to a little point, that's the same power, but now it's concentrated on a little tiny point, and the ant fries. Okay, or you can do it with paper. You burn paper. If I take that magnifying lens and I don't focus it, I just gave it defocus so the spot is large, all that energy is still there, but it's in a larger area. The moment I focus it, it gets focused down into one little spot and the paper starts to burn. Okay? Same thing with lasers. If I take a laser of a given power and I focus it down, it's a lot more powerful. It can cause a lot more damage. So, the other thing that's important when we're thinking about laser interacting with tissue is the wavelength. Why might the wavelength matter? Yes?
It affects what tissues are actually absorbing it?
Yes, it affects what's going to be absorbing it. Exactly. Very good. And how could the exposure time affect things? So if I got my laser on there for a second, or if I've got my laser on there for 10 minutes, how could that affect things? Yes?
The damage, or if the damage isn't cumulative, the effect is cumulative, so if you have more effect over a longer period of time, it causes more effect.
You're basically depositing more photons into that tissue. Okay? If that tissue is able to absorb those photons, then you get a greater effect. Now, if it's already pulsarized away and there's nothing there, then it doesn't matter. But if it's still able to absorb the photons, then you're actually increasing whatever effect it has on the tissue. And these things, the wavelength and exposure time and power per unit area, affect the temperature, right, of the tissue. And we know that the temperature of the tissue has a big difference on what happens to the tissue. If it's kind of in the 40 centigrade, 41 to 44, things start to slowly shut down. If it's more like 50 to 100 centigrade, things start to coagulate. If it's even above 100 degrees centigrade, you might have things vaporizing. Okay? And again, that temperature over time, those two things affect each other, because I can heat something a little bit. If I shine it for longer, it can heat it more and more and more, and it can lead to greater and greater damage. Okay? Now let's look at some examples of this types of damage. This is thermal damage. Okay? Primarily, things got heated up too much, too fast, and caused some element, some cells to die. This is a poor, unfortunate eye that stared at the laser a couple too many times. Actually, 1, 2, 3, 4, 5, 6, 7, 8 times. Okay? And the laser happened to be in different spots of the field of view, slightly different angles coming at it, and that's how you get all these nice little patterns. This happens to graduate students every once in a while. Hopefully never, but it does happen every once in a while that you get this kind of damage. Here's small laser burns and a little hemorrhage that got caused by a couple of the laser burns. Here you see more spots. Okay? Undergraduates and graduate students working with lasers have to always wear their eyewear, their safety eyewear. Because what happens is you tend to work with lasers that are not visible. You tend to work with infrared lasers a lot, or you might work with an ultraviolet laser. Okay? And what that means is you've got all these little mirrors lined up on your table, and these little magnifying lenses, and all these different things, reflectors, wave retarders. There's all kinds of things. I mean, there literally could be hundreds of things on one of these optics tables. And you're aligning them, and you're sitting there, and you're like, oops! I just moved the mirror, and it shined in my eye, and I just burnt a hole in my retina. Okay? Not so nice. Now, that kind of damage happens a lot with infrared. It doesn't happen so much with ultraviolet, because the surface of your eye will block the ultraviolet. But this can happen. And the difference is this. So, if you think about it, if you take a 100-watt lamp, you know, your little incandescent lamp, 100 watts, pretty bright, right? Kind of annoying, bugs your eye. But the size of the lamp, let's say you've even got a pretty small one, you've got a pretty concentrated bulb, okay? That's only 10 millimeters. That means you got a bulb like this, that's 100 watts. That's like one of those halogen lights, really bright. You know, remember? Little tiny bulbs, really bright. Your eye has a lens to focus the light. It focuses the light, and the spot size that happens on your retina is around 300 to 400 micrometers. The focus point on your eye, okay? If the light is about 5 meters away. So you're getting, something less than a millimeter in size spot on your retina of that light bulb, and that's registering as, ooh, that's a bright light. It's kind of bugging my eye. And that is about 150 watts per square meter. That's the amount of power delivered into your eye. 150 watts per square meter. Now, if I take a 1 milliwatt laser, and this happens to be a 5 milliwatt laser, okay? So 5 times as much energy, and I shine it into the eye from 5 meters, I get a spot that's focused on the eye of 2 micrometers. Notice this was 3 to 400, 2 micrometers. So now I've concentrated 1 milliwatt. This was 100 watts, okay? This is 1 milliwatt. Much, much smaller. I've concentrated it into a very, very, very small spot. The irradiance is now 300 million watts per square meter. Okay? So even though my original source was not nearly as powerful, it was the laser has the one thing that delivers all that power directly, whereas this radiates it out all over the place. Okay? And the way the eye focuses and it makes the spot size, you can get damage. That's why we tell you not to stare at these. You won't get it very quickly, but it's just not a good idea. Okay? And again, it has to do with So this is the main message, that the two sources can be, even the weaker source, if it's focused to a really, really small spot, can have a much greater potential for damage. Yes, there was a question.
I was just wondering with this specific picture right here where the person got like 8 pieces of damage, like to what extent is that damage? Is this person now blind, or do they just not see quite as well? Because that seems like really horrific, like, oh my goodness, 8 pieces of damage in my eye.
Go ahead. How bad is it, basically? Yeah. Okay. You guys know you have a blind spot in your vision? It's about the size of a quarter at about arm's length. There's a spot that your brain makes up. Okay? It just totally makes it up. Okay? This person now has to make up 8 of those. This person's brain, okay? So, and that's bigger than the size of a quarter. So it's probably have about spots like this at this distance. And they have 8 of them that they have to make up. So probably hampered, quite a bit hampered. And what they heard when this happened is they heard snap, crackle, pop. Because basically it was like when you take the egg white and you stick it on a really hot pan, and you hear that, it kind of makes that little noise as it congeals. That's what they heard here. These cells basically popped. They overheated and popped. Yeah.
So all of these damage spots came from a single point in time, or is it like 86 around?
What tends to happen is there are experiments where you create arrays of lasers. So probably what happened here is there was something that was radiating out in a couple of different directions at the same time. So probably it is one incident where it all came about.
You don't think the same kind of damage from looking like at a laser pointed somewhere else too, and see something in the eye?
Correct. Yeah, because when I do this, sometimes it's annoying. Looking at it, it's kind of bright, but it's already spread out quite a bit. Okay, it's already spread out more than if I just were to do this, and it's also being diffracted. It's scattering all over the place, so I'm not getting all the energy coming back to my eye. It's really going all over the place. Yes.
What about your eyelid? Like if you have a illusion, you can look towards your eyes. How does that affect it? Is it?
The good news is that most of us are smart enough that when we see a laser like that coming to our eye, we close our lid, and the response time that we have is fast enough that we don't cause damage. It very, very mildly, and again scatters and is mostly blocked. Because remember what happened with my finger? Green doesn't go through very much. Now the lid is thinner, so a little bit goes through, but much less. That's the other thing. It's a question of how much time you have to block out that. We're usually pretty good at we just turn away. Just turn away or close our eyes. That's usually what we do. The problem is when you can't see the laser beam. So another thing you can do is you can weld 2 tissues together. This is, I think this is pieces of aorta. Welded together, it's 2 vessels, just with coagulation. You can use the laser to heat up the junction and basically connect 2 vessels together. Yes?
Can you kill the tissue?
Well, what they did in this case is they actually put like a sugar on there, and they caused that to coagulate. And then the idea is that the tissues, the 2 things will actually grow back together. So it kind of just forms a seal, and then they can grow back. And this was the laser hair removal. In the laser hair removal, they usually use around 755 nanometers or 1064 nanometers. So those are both near infrared. And what they're counting on is that energy will be absorbed by your hair follicle. Okay? So those of you that have light-colored hair, it's harder for light hair to absorb that energy. Those of you who have dark-colored hair, it's much easier for that hair to absorb the energy. So laser hair removal type of techniques work much better with people with dark hair. The lighter you go, the harder it is for that to work. Just because I can't get very much energy absorbed by the hair follicle. Now, the amount of time at which I do it, I pulse the laser so I can keep the follicle hot while the epidermis has time to cool. So this energy is also being absorbed by the skin, okay, and layers of the skin. But if I pulse it, the energy, in a sense, has the most damage where it's absorbed the fastest and the most, which is in the hair follicle. And effectively, I heat up that hair follicle enough that the cell that has that hair follicle, the cells around it die. Okay? That's what laser hair removal is. Killing the hair follicle and the cells around the hair follicle. Okay? Does that make sense? The bad news is then in many states you don't have to be certified to operate one of these. And there's this thing that tells me how long am I going to pulse the laser, at what power, and how many times per second. Okay? If they have those set wrong, they'll scar you. They'll burn you. Okay? So ideally you want to know if somebody's been certified in using one of those machines before you actually go and get that process done. And you can do hair removal, skin rejuvenation, brown spot removal, spider veins. I can't remember. Did I show you this video of me sacrificing a hair on my hand? I'll show it to you real quick. Okay. So, if you take a digital camera, now what wavelengths did I say they use for hair removal? 750 or 1,000. Those are near infrared. Can our eyes see them? But my handy dandy digital camera can. Okay? So, here I sacrifice the hair on my hand. So first what they do is they cool the hair. They put a little piece of metal that's cold, and now watch. Okay, that was it. You saw the flash? Now when I was in the room, I saw nothing. But that flash was the reflection of the near-infrared laser shining off of my hand. And that's the hair right there. I hadn't shaved it, so what it did is it singed the whole hair. And it came back. I didn't want to really sacrifice it. I would have had to shave it and so that all the energy got concentrated in the follicle, but I didn't shave it, so all the energy got concentrated in the hair itself. Destroyed the hair, but didn't destroy the follicle. That's why they have you shave first before they do these laser hair removal procedures. Okay? And this is on a leg. This is for removing wrinkles. And you see all the flashes? That's the laser flashing. Again, in the room you can't see it. Okay? But because I have the camera that can see the near-infrared, I could see it. Reflecting, yes.
How does that remove wrinkles?
Okay, the idea for removing the wrinkles is that basically I heat up the tissue and the collagen fibers kind of stretch and realign when they cool.
And they stay that way and don't go back?
They should stay that way. I mean, over time, they'll come back. But, yes?
Do people ever use it to remove, like, scar tissue, like the side of stuff?
They do. They use it to remove scar tissue. Port wine stains, like big red stains. I don't know if you guys even know who Gorbachev was? Okay. Gorbachev used to have this big port red wine stain, those kinds of things. They remove it for that. Certain types of acne. It can be used for, it works best for things that are sealing of surface vessels, things like that. That's where it works best. And then they kind of get closed, or for tightening. Okay? Now, I'll go through a couple more of these. You can also produce a plasma. You can pump enough energy with your laser that you cause basically an explosive vaporization or cavitation. So you basically create a plasma with a laser, and you do it very, very quickly. You put a lot of energy in a very small spot. Okay? And what that does is it creates a quick bubble, but then when it collapses, it creates a shock wave and it breaks things near it. Okay? Let me show you some more things here with that. I thought I had. Okay. That explosive vaporization basically has to do with the fact that you have to get the energy into the system and it has to dissipate. When you turn the laser off, that energy has to dissipate somewhere. And what it does is it basically causes the particle that it's near to break. And what do we use that for? We use that to remove tattoos. Because the large particles of pigment in the skin explode, resulting in smaller particles, and your body absorbs those smaller particles, and the tattoo is gone. Okay? Here's the example. This person went through a process of 8 months to go from that to this. Okay? Notice it isn't completely removed. It's, somewhat removed. And notice that certain colors went away better than others. Okay? Like the red went away pretty well. The blue not quite as well. And the black in the center went away well. But what happens is this is your skin. You have the surface, which is the epidermis, the dermis, and the hypodermis. And what they basically do, we slough the surface all the time. It comes and goes. That's why you put a temporary tattoos, over time it's gone. Okay, or you write with a marker on your hand, over time it's gone. What they do when they make a tattoo is they take a little needle and they go underneath and deposit that into the dermis. The dermis doesn't get replaced. That's why it's permanent. So when you want to get rid of it, you basically use a medical laser. It has to be absorbed by the epidermis and make it into the dermis. And the energy has to be deposited in the ink. And the way you do with it, you do this explosive vaporization that causes the ink particles to blast into little pieces and then get reabsorbed by your body. But they do cause some scarring. I mean, well, not so much scarring, but they do cause some temporary damage as you're getting the process done. You can also use this cavitation to break stones, kidney stones. You can go inside with a fiber optic to where the stone is. You can make these fast pulses of the laser. That again causes this cavitation, which causes the stone to break up into little pieces, and hopefully the pieces are small enough they can flush through your system. Okay? Now, I can also use photomechanical. So in this case, I can use a laser to remove stains on a tooth. Okay? But if I use too much power, this is what happens. I crack the enamel. Okay? So this is where it's very important to deposit the right amount of power over the right amount of time, and it's going to depend on the surface. You can get this nice kind of mark like this, or you can get this. Okay? That's all just depending on the amount of power delivered. And then there's photoablative. Photoablative takes advantage of the fact that if I put enough energy in there, I can make, if the electric field associated with the light is higher than the binding energy between molecules, I can make the molecules fall apart. Okay? This is that idea of ionizing radiation that we talked about on the very first day. If I have enough energy in there, I make the molecule and the atoms just basically fall apart. The electrons disappear. Okay? They go away. And so what happens is, with that, molecular bonds are broken and the components are vaporized without generation of any heat at the edges. So you have to use very energetic wavelengths. In this case, we use 193 nanometers in the ultraviolet. And it doesn't go very deep. So we use this on the cornea. And this is where I'll stop here. We use it on the cornea. We strip back the top part. And then we come in with our laser and we reshape the cornea. This is showing you the flap and the reshaping. And then we put the flap back on top. We reshape it so that the light will be focused differently, such that you won't need glasses anymore. And the way this laser works, it's an ultraviolet laser. It only penetrates a few layers of cells and basically vaporizes them, makes them go away. Okay? This is showing you from the side what the vaporizing of cells looks like. Okay? I'll leave it here. I'll pick up from this on next Wednesday. Okay? So you guys, good luck with your reports. Feel free to email me any questions you might have. Okay?